Okay, let's look at Chapter 10 of the Whit and Whit book. Begins on page 209, and the title of the chapter is Introduction to Hypothesis Testing, the Z-Test. Let me just say an introductory word or two about hypothesis testing and what it is and why we do it this way. A hypothesis is a statement, not a question, but a statement, to which we're going to test and see if it, for lack of a better phrase, holds water. It's a potential answer to the question. So we ask a question, we say, here's what the answer might be, let's see if that works as an answer or not. That's essentially hypothesis testing. Now, did any of you, some time when you were a child, or maybe, did anybody go through the allergy testing regime where you go to the doctor and they put all these 100 and some dots on your back? Okay, what that's doing, that's the same, yeah, I'm getting a lot of yeses on that one, I always do. That's the same essentially as testing a bunch of hypotheses. Now what happens is the doctor asks you all kinds of questions about habits and lifestyle and diets and things like that. And he thinks, well, you know, it sounds like that you might be a good candidate to be allergic to this or that or the other. So he comes up with all these things that kind of are his best guesses based on your answers of things that you're to some degree likely to be allergic for. So he puts all these dots, these little pin sticks all over your back, and each one of those little dots represents the possibility that you're allergic to something in particular. One dot might be that you're allergic to grass. One dot might be that you're allergic to some kind of food, or you're allergic to watching certain TV shows on, I don't know, silly things almost, but they get pretty specific. So each dot represents a hypothesis or a possible answer that you are allergic to such and such. And depending on whether the dot turns a color or not, that gives him the answer. So he's testing hypotheses. Now, it may or may not be true. There are things like false positives and false negatives, so it's not necessarily the answer. Now, you remember one of the statements I made the first night in class is that this kind of research doesn't prove anything. It just simply indicates that the degree to which something is likely. Let's say, let me set aside my own rule for. Let me use the word prove for a minute just to illustrate a point. I'm walking through the woods. It's a bright and sunny day, and I'm walking through the woods and I see a nice patch of flowers, and all the flowers are yellow. And I walk along a little more and I see more yellow flowers, and I think to myself, all flowers are yellow. Now, I don't know if they are or not. Pretend. Is it easier to quote-unquote prove that all flowers are yellow, if in fact they are, or is it easier to quote-unquote prove that not all flowers are yellow? If it's true one way or the other, it's easier to indicate that they're not all yellow. So, I've got two statements. All flowers are yellow. All flowers are not yellow. The statement, all flowers are yellow, is a hypothesis. We generally talk in terms and test in terms of null hypotheses. That would be the example of all flowers are not yellow. What I'm getting at, and the reason we do that is because it's generally easier to, here's that dirty word again, prove. It's easier to prove something isn't true than to prove something is true. So we set things up in terms of null hypotheses. Follow that okay? So that's the first kind of that's the first introduction I want to make about hypothesis testing. We're gonna run through a few here in a little bit. We're going to talk in terms, and I've used these words earlier. Common and rare occurrences. If you look on page 211 of your book, And again, I don't know if this is helpful or not, but a common outcome, I'll read it and then I'll kind of turn it into plain English. I'll translate. A common outcome is an observed sample mean qualifies as a common outcome if the difference between its value and that of the hypothesized population mean is small enough to be viewed as a probable outcome under the null hypothesis. Any questions? A common outcome means this. If you're looking to see if there's a difference between two things, the difference isn't enough to get excited about. It's like if I flip that coin, I'll say 100 times. If I flip that coin 100 times, I would expect 50 heads. Probably not going to get exactly 50. If I got 49, I'm not going to get too bent out of shape about that difference. I expected 50, I got 49. That's close enough that 49 would be viewed as a common outcome. It means things are close enough together to, okay, that looks reasonable to me. A rare outcome, again, I'll read the definition again. This sounds almost as good. An observed sample mean qualifies as a rare outcome if the difference between its value and the hypothesized population mean is too large to be reasonably viewed as a probable outcome under the null hypothesis. Okay, that means that the differences we were talking about a minute ago is big enough to make us want to go, a rare outcome. So we flip a coin 100 times, we get 49 heads. Okay, that's a common outcome. Close enough. If we flip that coin and get 100, I'm sorry, we flip that coin, let's say we get 99 heads, I'm going to go, doesn't look like a fair coin to me. Now, is it possible you could randomly get 99 heads? And the answer is yes, but not very likely. Not likely as in a low probability. So that would be a rare outcome. Now, the question in terms of what's common and what's not, if I look at the normal curve, and we remember what we've learned or talked about the normal curve, do you remember when we were doing correlations and we said we look for the p-value or the significance level is 0.05 or less? That's 0.05 means 5%. Again, that was a little introduction to this too. If I've got a normal distribution, and I do from the sample, the sampling distribution of the means, if I've got a normal distribution, and I'm going to look at the 5% on the ends, in that case, I might look at the lowest 2.5% and the highest 2.5%. That would be the 5% that are what we might refer to as outliers. So what I would do if I got, and I'm going to say I'm going to randomly get a sample and compute a mean or whatever. If I get something that's over here on the extreme right or the extreme left, the area I've kind of badly shaded, that would be an example of a rare occurrence. If I get anything between those points, anything in the unshaded area, that's common. That's not going to be enough of a difference to get excited about. It's not going to make me want to go, The shaded area, I want to go, So that's the difference in common and rare. You will remember, because I command you to have remembered, that we talked about a little bit about error and the standard error. Somebody nod and say yes and pretend like you remember this. Question: are we supposed to do? Let's see. Yes. Were you not? Well, were you not seeing anything on the board? Okay. Let me see if I can do that again. Oh, I know what I'm going to do wrong. Okay, let me go back and do it. Sorry about that. I didn't do this. Let me just real quickly say the highlight. Okay, now you're seeing it. Okay, yeah, I was talking about the shaded area that you didn't see would be an example of a rare occurrence. If I'm in that extreme 5%, either the lowest 2.5% or the highest 2.5%, generally, that would be rare. Anything in the unshaded area would be common. Okay, so yeah, thank you for pointing that out. Okay, now we talked about error. And we specifically talked about standard error. We called it standard error of the mean. And if you remember the formula, the symbol is a lowercase sigma sub x bar, standard error of the mean, as in x bar as in mean. It is based on two things. It's based on the standard deviation divided by the square root of n. So again, recall that the larger the n is, the smaller my standard error is. The less likely I am going to be off. The larger my n is, the more likely it looks like the population looks. Therefore, the less likely that I have error in there. And we also know, and again, I won't belabor this point again, but error, it tends to be normally distributed. Now, let's talk about, there's an example. Actually, the example is kind of spread throughout this chapter like I told you it would be. We know that the SAT has a particular mean and standard deviation, and we're using the SAT as a mean of 500, and the standard deviation, or that symbol, is equal to, I think we're using 110. We've used 100, we've used 110, depending on the example that it gives us. Okay, so let's say that I'm principal of a high school, and 100 students take the SAT. What is the standard error for that situation? My n is 100. My standard error is going to be the standard deviation, which is 110, divided by the square root of 100. My standard error is going to be 11. And by being normally distributed, I know that I can draw a normal curve like I left myself a lot of room for. I can draw a normal curve, and I can talk about plus 1, 2, or 3 standard errors above the mean, or I can talk about 1, 2, or 3 standard errors below the mean. Because, again, error tends to be normally distributed. We talked about how, you take an imprecise measurement of anything. Sometimes your measurement's a little higher than it ought to be. Sometimes a little lower than it's going to be. If you take a bunch of measurements, probably that error kind of cancels out. It's kind of like the end's a little small, but the old saying, when you're building something that involves cutting wood or whatever, measure twice, cut once. You might have messed up the first time. So increase the n. That increases your likelihood of error. If you look on page 212, they do a much better job of drawing what I tried to do on my normal curve a minute ago, but in terms of common or rare. Let me also add that in terms of common or rare, let me put that together with what I said about null hypotheses a minute ago. Common or rare. A rare occurrence means we reject the null hypothesis. We usually abbreviate that as a H sub O. A common occurrence means we do not reject. You do not reject the null hypothesis. Let's say, for example, I've got my two teachers, classroom A and classroom B, and I've got class averages of, say, 88 for A and 82 for B. Is 88 and 82 a significant difference? And I don't know. It depends on a lot of stuff like variability and stuff like that. If that difference of 6 points, is that difference of 6 points a big deal? If it's not a big deal, it's a common occurrence. Say, no, there's not a big difference here. Now, how do you know if it's 6 points is big enough or not? Stay tuned. We'll get into that just a little bit later. If it is a big difference or a significant difference, we would reject the null. The null would be, the question is there a difference between A and B? The null would be, there is not a difference between A and B. So what we're trying to do, and here's where we're going to get really, really bogged down in double negatives, and I'll try to let these cancel, like sort of shave off these as we go along. But the null hypothesis is there's not a difference between A and B. If I reject the null, it's not true that there's not a difference. See my double negatives? I know, I just blew everybody's mind. It's not, if I can determine it's not likely true that there's not a difference between A and B, I'm rejecting the null, and I'm in effect saying, hey, there probably is a difference. That's what I mean by the double negatives canceling each other out. But technically, we test null hypotheses and try to reject them. So I reject that there's not a difference. Oh, it must be a difference then, because remember, walking through the forest on a bright sunny day, I think all flowers are yellow. I can discredit that. So I can discredit or quote unquote disprove something more likely than I can prove something positive. I can disprove something negative, or I can discredit something negative easier. So we try to reject null hypotheses. Questions, comments? Again, just follow me for now. We're getting to the mechanics of things here pretty quickly. So that's the framework that we're going to examine, that we're going to try to deal with hypothesis testing. Now, do you remember, again, in a universe far, far away, the standard scores, the z-scores? Remember that a z-score is equal to a particular score minus the mean divided by the standard deviation. And that tells us how many standard deviations above or below the mean that an individual score is. Let's say I've got this situation. Remember my 100 students? My average for my 100 students is 533. What do we say the average, the SAT? The average, the overall average for the SAT is, and what is how much? 500, you said? What do we call the population mean? It's not the mean. It's not X bar. X bar is just the mean for my 100. Yeah, you're writing in the air. I'll try to. Yeah, you're writing sort of like this, sort of a little curly Q. You pronounce mu. Mu, kind of like cross between the cat and the cow, I think. You know. Okay, so the population mean is 500. The question is, hey, my kids scored 533. That's pretty good, isn't it? And the answer is that I don't know if it is or not. It's certainly above the mean, but is it enough above the mean to get excited about? Or is it, in other words, is it significantly higher than the mean? In yet other words, is it a rare occurrence? Now, Let me go back to that z-score. We also have something called the z-test or the z-distribution, or or they got the book called the z-ratio, and it's based on the kind of format, except that the z-score that I've got in front of you, I have involved a particular individual score. The z-ratio is not comparing a score with the mean. It's comparing my mean, the sample mean, with the population mean. So I don't have any individual scores involved here. I just know that my mean is 533, the overall mean is 500. How do those compare? Okay, 533 is higher, but is it enough higher to get excited about? Okay, so what we do is we make a calculation based on our individual z-score. So the z-ratio, and keep in mind this is to compare sample means with population means. So the z-ratio is, again, I'm still going to call this z, but I've identified it as a ratio, not just a particular score, is my mean minus the population mean. That tells us how many points above or below we are in terms of the population. In our case, 533 is 33 points above 500. I divide that not by the standard deviation, but by the standard error. So I'm calculating a z-ratio. So in our case, our x bar is 533 minus the mu is 500, and it's on the other screen. Do you remember what our standard error was a minute ago? It was 11. So I hit the right buttons on my slide rule, and I found out that z-ratio is a 3. Now, if we think about it, or if we remember the right things, we can answer our question, is this big enough to get excited about it or not? That means we're more than 3 standard errors above the mean. And that's going to be rare because that's going to be in that 2.5%. Do you remember that? Remember where that 95% break is? It's plus or minus how much? Approximately. Approximately plus or minus 2. Approximately. We're going to get a little closer in just a minute. Well, I know, so I'm going to compare my 3. I know that's going to be up here somewhere. That's a rare occurrence. Therefore, I can say, it's pretty likely that my 100 students just, blew the national population out of the water. Let's be a little more accurate. I wish I had a bigger board to write on, but I don't. So keep in mind, I'll write this part again. Keep in mind and that the standard error of the mean is the standard deviation divided by the square root of the mean. Scroll with me back to that table we were using earlier for the normal curve stuff. Remember I told you this normal curve stuff would come together here. Go back to page 530 and 531, and that's table A. 2 pages, 3 columns each table. And I want to know at what point I get into that upper 2.5%. So if you look at the B column, scroll down those sets of B columns until you see 0.025. I'm sorry. Yeah. No, I'm sorry. Not 025. 0.475. Yeah, because it's going to be, yeah, the 025 is going to be in the C column, but yeah, B column is going to be 0.475 because that's the right half minus the 2.5%. And what Z does it take to get onto that far right 2.5%? And the answer is 1.96. 1.96. I said it was about 2, and we said we're going to be a little more accurate. Yeah, it's pretty close to 2, but it's really closer to 1.96. So, if I've got my normal curve again, and I'll examine where plus or minus 1.96 is, and my rare areas are on those two tails, the left tail and the right tail, and my, as I calculated a minute ago, my Z was 3. That 3 is above 1.96. That's in the shaded or the rare area. So that's enough of a difference to say that probably is a real difference. It probably wasn't just you happened to select your top 100 students to take the SAT. If they were randomly selected, like, and it's not from state to state, but with these data, your score of 533 is significantly higher than 500. 533 is significantly higher than 500 because I had to take into account error and kind of the scholarly word for error is sort of wiggle room. If you look at the shaded box at the top, page 215, it kind of works this out. Let me call your attention to just a couple things on there. The decision rule. We said that most educational research is conducted at the 0.05 level of significance. That means you're looking at that 5% that's rare. And we found out that it's in the rare 5%. It could be on the high side or it could be on the low side. That means Z is either greater than 1.96 if it's rare on that side, or Z is less than negative 1.96 if it's rare on the low side. Well, our Z was 3. Because that 3 is larger than 1.96, our mean is significantly higher than the population mean. And their interpretation, they say, gee, even in more plain English than I do, just about for a change, the mean SAT score for all local freshmen exceeds the national average. That's enough of a difference to get excited about. What if our average for our students had been 501? Probably would not have been significant. Probably not larger enough to get excited about. The bump, what do you mean by the question, where's the bump point? I'm waiting to hear what bump point means. Oh, if this number is larger than 1.96. If this had been 1.97, yes. If it had been 1.95, no. So the 1.96 is your bump point as you've described it. That's the decision rule. It says almost in the middle of that shaded box under decision rule, reject it. We reject the null that there's not a difference. The null would be there's not a difference. We've rejected the null because 3 exceeds 1.96. It's on the outside, either the far left or the far right. Other questions? Keep them going. That's good. Yes. And the question is, we went to the table, the back found the 1.96. You don't ever have to do that again unless you change your situation. We know it. We know 1.96 is the, I like that bump part. We know 1.96 is the dividing line between rare and common at the two-tailed 0.05 level of significance. And I'll talk more and more about ones and two-tails in a few minutes. Yes, two-tail question was this were two-tail, and the answer is yes, because okay, sneak preview of coming attractions. I'm going to change lessons here in a minute, but there are two ways I can ask the question. Here's the difference between these questions. Is my mean higher than the population, or is my mean different than the population? It matters the way I ask the question. And that's what we'll get into when we talk about one and two-tail tests in a little bit. Other questions, thoughts, comments about? The question was what if you change? What do I mean by if you change your situation? This was a two-tailed question. If I ask a one-tailed question, that would make a difference. Yes, you're getting so excited and so ahead of ourselves. Another way we might change our situation is, let's say I'm not happy with the 0.05 level of significance. This is life or death stuff. I want to go to the 0.01 level of significance. I would get a different magic number. 1.9. Right? We'll call that later critical value. There's a term I wasn't going to introduce for a while, but okay. The question was, you said, are the only two-tailed ones the normal curve? Well, if you whether you've got a curve that's normal or not, there's going to be a lower and upper tail. But right now we're just talking about. Remember, we refer to this as parametric statistics, which has to do with the normal curve. So right now it doesn't matter. Right now that's all we're dealing with anyway. Any other questions here or home? Y'all aren't saying much there tonight. The question is H sub 0. The H sub 0 means the null hypothesis. My H sub 0 in this situation was there's not a difference between my score and the national scores. It says H sub O is the null hypothesis, as in O being like 0 meaning like null or nil or nothing. Okay, I'm going to do one more example. That's okay. If we're okay so far, so good. And let's walk through on page 219. The bottom where it says project check 10.5. Again, keep in mind that Z is the sample mean minus population mean divided by standard error. And standard error, keep in mind, is the standard deviation divided by the square root of the sample size. Okay, so read with me, walk through with me. Progress check 10.5, bottom of page 219. According to the APA, American, so that's the good folks that bring you the APA stuff that we have to write by. You love them already, I know. Members with a doctorate and full-time teaching appointments are on the average of 82. I am in the wrong department, obviously. $82,500 per year. That's everybody. Therefore, that is our mu. Everybody earns 82. Altogether, the population's mean is 82,500, and the standard deviation is 6,000. Means it's pretty well spread out. I mean, for example, we'd know that if you're earning more than one standard deviation above the mean, you're earning, what, 88.5. And we know that about 16% of the people do that. Okay, that's everybody. The situation we're going to look at is I'm looking at just female members of the society, and the female members earn an average of 80,100. So that is my X bar. 80,100. And that is from a sample, random sample of 100. Oh, it's nice that they give us these neat numbers to work with. So my question is 80,100? Let's see, where's the question? Okay. Does it appear that overall women earn less than average? And don't answer yet because we don't know. Yes, 80,100 is less than 82,500, but is it significantly below that? Is it enough of a difference to say, hey, that looks like a real difference, not just because I sampled the wrong 100 people or something? First of all, okay. Well, first of all, what is our standard error? It's the standard deviation, which is 6,000, divided by the square root of 100. Now, if you had, let's say we didn't have the standard deviation of the population, we just had the standard deviation of the sample, which we don't have, you'd use whichever one you have. It's better to use the population if you have it, but sometimes you don't have it, you just have the one for the sample. So this is going to be, my slide rule tells me 6,000 divided by 10, so that's going to be a standard error of 600. Is that right? Okay, so my standard error is 600. Hang on a second. Let me see what make sure I'm going to see what I ask you to do for homework. Okay. Okay, very good. Okay. All right. So I've got my standard error. That goes into factoring what the Z is. So the Z is 80,100 minus, that's the sample mean, minus the population mean of 82,500 divided by the standard error of 600, which means 80,100 is what? Minus 2,400, which means women are earning $2,400 an average less than everybody. So we divide that by 600, and I find out that my Z is -4. Now, do you remember what our comparison number was? It's the same number. The comparison number is plus or minus 1.96. Well, it turns out women are earning 4 standard errors below the average. That's a significant difference. They're earning significantly lower. Now, what does this mean and what does it not mean? Because I've got all kinds of problems with this setup of this study, the design, and also what you may or may not conclude. First of all, does this mean that we're being discriminatory? Yes, women make less than men. Does that mean, hey, this person's a woman, I can pay her less? Does it mean that's what I'm doing? No, again, because remember, this tells us what it is. It doesn't tell us why it is. It just tells us that women are earning less than average. It doesn't say they're earning less than average because of discrimination. The other problem I have with this is the research design. We're comparing the average of women with the average of everyone. Can anybody see a problem with that besides me? What's your problem? Okay, the point was, I don't know what the proportion of women is to the total population. That's true. Let me paraphrase that the way I would put it, is the average of everybody includes women. Why don't we compare women to men instead of women to the average? Because women are included in what you're comparing to. Wouldn't it be a better comparison if you compared men to women? Now, in this case, since the average is higher, therefore men must be higher, it's probably going to be a z of even less than -4, but that would be a better number to work with. But the bottom line is that, yeah, this appears that it's likely that women are being paid less than men. But don't overinterpret that into saying why that might be. And again, I'll probably come up with a little better design than they've laid this out. So our null hypothesis would be that women are not making the same as men. The salary of men, try again, Don. The salary of women is not the same as the average salary. We're going to reject that. Therefore, it is different. I'm sorry to say that again. Null hypothesis. Yeah, because I think I said it wrong. The null hypothesis would be the salaries of women are not different than the salaries of everyone. We have rejected it. Therefore, the salaries of women are different. And the way they're different is that they're lower. Exactly the way I just said. The salaries of women are lower. Now, sneak preview of coming attractions, and I'll put this into the list, but we did this as a two-tailed test. I'm going to elaborate a little more on the difference between one and two-tailed here next time. And yeah, your homework question is going to be a lot like this. Any other questions, thoughts, comments? We reject the null that there's not a difference, therefore there is a difference. So you're trying to go back to those double negatives on me. Yeah. Okay. Time to take a deep breath. Okay to close this session out? Okay, very good.